Okay, now I want to consider like a toy example that's like very common and very simple, but it helps us a lot to understand the influence of gauge potentials in quantum mechanics. So I want to consider electron on a ring. So something like that. So there is like some electron on this ring moving around, I don't know, in some way or another. And what we want to add on this problem is, so we want to put a solenoid inside. Like this is phi, and the solenoid so means so B is non-zero inside this little region, but B is zero outside. And classically, classical electron only knows about Lorentz force. F is equal to Q over C, V cross B, and if B is zero, this electron should have no influence from the magnetic field inside. But in the quantum mechanical case, we have seen that it is the vector potential, not the magnetic field, that enters the Schrödinger equation. So then we have to try to understand what happens to this problem in the presence of this flux. So first, let's set up the vector potential. A. It is more favorable to use cylindrical coordinates. So for that, I'm going to use R component of A, theta component of A, and Z component of A. I'll write in this curvilinear coordinates, and we want to find what this is. But to find this, we can consider the line integral of vector potential around some any loop, but around the loop of the electron. So this is dl dot A, and this is going to be equal to what? How do we calculate this? So this is only the loop, right? And we are going to say A is constant around the loop. So then it is going to be 2 pi r times, okay, r, let's call this radius r, 2 pi r times a theta on that location. But I can rewrite this by using the Stokes theorem. By Stokes theorem, this is going to be converted to an area integral, which is going to be the sigma dotted onto curl of A, but curl of A is B, and area integral of B over all the region is what? It is the total flux, right? Then combining these two, what we find is A theta is equal to total flux divided by 2 pi r. Now we want to write the Hamiltonian verse. Let's first start with the classical Hamiltonian without A, and then let's try to see what happens if we turn on A. So classical Hamiltonian H is equal to, so there's angular, it's like p squared over 2m, but this is like a rotational motion. In the rotational motion, p is replaced with L and m is replaced with I, and I in this case is just a point particle, m r squared. And in quantum mechanics, L is going to be replaced with, of course this is in classical mechanics also, but P is going to be minus I h bar R cross nabla. And let's write this in R, so So this is theta and this is z, and this is going to be del r. So this nabla you can look at Wikipedia. This is 1 over r del theta, and this is del z. But in this problem, you can see like we can use right-hand rule, right? So this is circling around this, and the only angular momentum is by right-hand rule, angular momentum along the z direction. So we care about the z component of this object, and it is going to be minus I h bar. So this is r gun del over del theta minus theta del over del r. But the particle is constrained to move on a ring, and there is no change with r, so this is going to be 0. At the end we have minus I h bar del over del theta. And of course this is the angular momentum we know in like in cylindrical coordinates, right? That's just the angular Laplacian. Now we want to introduce vector potential. In this case, L is going to be R cross P minus Q over C, and there are other components, but we care about theta component. Theta times, let me write it like theta dot, and so this P we already found is going to be minus I h bar del over del theta. Actually, let me combine everything, like this is going to be theta component. And we are interested in electrons, so Q is minus E. Minus is going to plus, so this is E. And this R is going to be R, which is fixed on the radius, and all the cross products are going to be here. R cross theta. But R cross theta is, right, so this is Z, right? So this is theta, this is R. If we take, it's going to be Z hat. Then I can write the Hamiltonian. Hamiltonian is Lz squared over 2I, which is going to be 1 over 2m r squared minus I h bar del theta plus E over C. We found oh, I think I missed like a, so there is, okay, there is like R here, right? When I take the R here, I think I need to also multiply it here, R, because it's multiplying the oh, actually it is not. So yes, I think I need to just write this a little bit carefully. Let me not skip the pieces. Let me write it like this. So L is R cross P plus E over C times A, and this is going to be R cross P. This piece we calculated, plus E over C R cross A, and so this one we calculated. This is minus I h bar del over del theta. This one is E over C. So this is, we only need this, right, on the ring. So this is going to be R times R hat cross, and A is going to be A theta times theta hat, and I'm going to write this A theta here, A theta. So this is going to be R cross, right, and this is also a Z component. So this is also Z. There's an additional R here. So this is minus I h bar del theta plus E over C R A theta entire thing along z direction. Okay, I think that's now correct. Now Hamiltonian is Lz squared over 2 m r squared, which is 1 over 2 m r squared times the square of this thing. So this is the square. Now I can write what I found for A. So A of theta was found to be like this here. So let me push this a little bit. A theta, so this is A theta. And cancel that with that. And I want to take one h bar out, so this is okay, let me copy this because I can miss some factors, and let's compare. So I want to take one h bar squared here, h bar squared, erase this. I need to have h bar here, so I cancel that, cancel that. So this h bar has 2 pi, I will cancel it with this one, so this is 2 pi and no h bar anymore. I think this is correct, right? This is right.
The partial derivative with respect to theta, that part.
So there was only h. This is minus I h bar del del theta.
So that must be 1 over h bar.
But so there's h bar squared, right? I took out h bar. Yeah, yeah. Because of this square, I took out h bar squared, and I think this is correct. And here I want to define a flux quantum. So let's define flux quantum phi naught is equal to hc over E. Then this Hamiltonian becomes h is equal to h bar squared over 2 m r squared minus I del over del theta plus, let me call this beta squared, where beta is equal to phi over phi naught. I just redefined this and I put it in that form.
But there was also
2 pi here cancelled the h bar, right? I brought, this was like h bar, 2 pi, and this 2 pi, yeah. And that's the official flux quantum. It is defined without h bar. It is defined in terms of only natural constant h, c, and e. Now I want to find the eigenvalues and eigenfunctions of this Hamiltonian operator. So we have to find this times some phi, which only depends on theta, should be equal to E times psi of theta. And we can like try an ansatz of the form e to the I don't know, gamma times theta, but from the periodic boundary conditions this should be equal to e to the I gamma theta plus 2 pi, right? Because if I go around the ring, I come back to where I was, and for this to happen, gamma should be an integer, and for that we are going to use gamma is equal to m, which is an integer. 0 plus or minus 1 plus or minus 2, which is usual angular momentum in the spherical harmonics. Phi m of theta is 1 over 2 pi e to the I m theta, and eigenvalues are going to be, let me write it like em is equal to this thing. So I'm going to write Im wherever I see this. So this is Im minus I times I is 1. So this is going to be m plus. And I want to see for each given flux what is the spectrum, and I want to change the flux and see how the spectrum changes as a function of flux. For example, for beta is equal to 0, I have m is equal to 0, there is like a 0 energy, there is like m is equal to 1, and minus 1, m is equal to 2 and minus 2, and so on. And as I change beta, I want to see how these individual levels change, and do they cross or not.
M and beta seems independent.
Yes, they are independent, and I want to do the following. So I want to do this beta versus E, for example, 1, E2, and E3, and so on.
But I mean, if you take this m plus beta as a single variable, then it will just be a parabola.
Exactly. Yes. But there are like different levels, right? So there's okay, exactly. Let me actually. I don't need Mathematica. Let me do this. So if I have m is equal to 0, it's going to be just a parabola, exactly like you said. And so this is a parabola. So this is E0, and this is beta, and for beta is equal to 0, I have a parabola. For m is equal to 0, right? M is equal to 0. There is like a parabola, and minimum of parabola is going to be at 0. So this is E0. But for E1, this parabola is going to be shifted like this, right? Now, so this is 1. So this is beta 1 is beta is equal to 1, right? So if m is minus 1 and beta is 1, it's again 0, and I need to shift it like that. So this is minus 1, right? This is so this okay. This one is E0. I think this one is E1. This one is E minus 1, and so on. I can change it like that. So there's another one. This is minus 2 and plus 2. I think it is easier to see it in Mathematica, but the point is the spectrum is periodic in beta, right? You just go and come back and go and come back. So let me write it because different, for example, E0 becomes excited state here, whereas E1 becomes ground state here. Whereas here, E0 is ground state, E1 is excited state. This is kind of like Bloch bands, but in a different context. So spectrum is periodic in beta. So E of beta is equal to E of beta plus 1. But I'm not putting the indices because levels change as you go from one beta to another one. So we can calculate the currents. Let's calculate current. So J is by definition minus E psi P over M psi. But in the presence of a vector potential, P is going to be replaced, minus E over M. So this is psi. So this is P plus E over C times A times psi. And this is going to be minus E over M. So this is psi. So this is minus I h bar del over del theta plus E over C. Let me just write what we had there. This was R times flux divided by 2 pi R times psi. And okay, this R is going to cancel this, and I'm going to take h bar to here, so this h bar is gone, and I'll put like an h bar here, and I'll erase the bar of h, and it will go with this, and at the end this entire thing is going to be cancel that, so this is going to be phi over phi naught, but we call this beta, so this is beta. And if this thing is acting on eigenfunctions, this is like e to the m theta. It is going to give us minus e h bar over m m plus beta. So then the current, okay, this is the current, and we can see current is going to be minus del E m del beta. I think I found something like this, but 1 over c del E del phi. So what this says to us is like, okay, so if beta bigger than 0, right, and if beta is bigger than 0, I have okay, this is the spectrum like this, and we are considering, okay, this is beta is equal to 0, and we are considering small and positive beta. Then we are going to be on this point, and that means j is going to be less than 0. And if j is less than 0, right, so this is, there's like a flux, and the current is on the other direction, and so this is the external flux, but due to current of the electron, there is a current is going to generate its own flux, and it's going to be against the external flux. That's why we call this, and we can do it on the other sign too. If beta is negative, so negative is going to be positive, and j is going to be bigger than 0, then we call this is going to be a diamagnetic current. Okay, so that was a small exercise to see what happens in the presence of a vector potential. Now I want to consider so-called, and after that let's finish today. So this is Ahoronov-Bohm effect. Which will be related to this closely. So let's consider. Well, let me consider like a circuit from freshman. It is something like that. And if this one is R1, this one is R2, we know that Req to the minus 1 is going to be 1 over R1 plus 1 over R2. But rather than that, if you consider conductance, Geq is going to be conductance from arm 1 plus conductance from arm 2. But this is, what does this say? This says that this is like a classical electron. Classical electron can go through arm 1. So this is what I call arm 1. This is arm 2 or arm 2. And the probability to go through R1 and probability to go through arm 2 is just added, right? This is just an additive relation. So then probabilities add. But we know electron is a wave. So electron is a wave, and we need to think about what happens if we take the wave phenomena. And in the case of wave phenomena, we can consider like a double slit experiment, something like that. And you are sending like an electron through a double slit, right? And there you have like a screen here. So the electron can go through slit number 1, or it can go through slit number 2. And we know, so if we call this psi1, if we call this psi2, probability to see the electron on a point on the screen is going to be, total P is going to be psi1 plus psi2 squared, right? We add the amplitudes, not the probabilities. And this is going to give us, psi1 square, absolute value, probability to go through 1, plus probability to go through second one, plus 2r psi1 star times psi2. And this last term is what we call interference term. And in this classical circuit, at the moment, we don't have any interference terms. So this is a double slit experiment for the electron. And now we can think about putting like a flux tube right behind this center, like this, put like a flux here, phi, and ask, and the flux is only behind the screen, so it is not, there's not going to be any Lorentz force to the electron, but we just saw from the phase, there's like a phase shift in the electron, and we may ask what is going to happen in the interference pattern. And just for reference, I think initially it is going to be something like that, right? Before the flux is turned on, it is going to be, I don't know, something like that. And so on, right? It's just usual interference pattern. But in the presence of flux, phi1 is going to be phi1 times e to the I, some additional phase, and this additional phase, phi1 is going to be, let's q over h bar c, some path, let me call it path 1, the L dot A, and similarly psi2 is going to go to psi2 times e to the I, phi 2, and phi 2 is going to be the accumulated phase through path 2. And now we ask, how does, okay, so this last term knows about the phase differences between two paths. And we want to see how does the total phase difference change in the presence of vector potential. And in the presence of vector potential, you can see one is psi star, the other one is psi, and the total phase is going to change like this because of phase change is going to be phi 1 minus phi 2 because we have complex conjugation in the second one. And that thing is going to be equal to, okay, I think this is 2. This one minus the second one.
I guess it's phi 2 minus phi 1.
Yes, I think phi 1 minus, I wrote phi 1 minus phi 2, right? But you can take the other one, or like if you want, there could be an overall minus, that's also fine.
The only thing changes is the sines and cosines.
Yes, but this is through path 1, this is through path 2. Right? These are different paths. But what we can do is like we can, so one path is positive, right? We go through path 1, and negative of this path is going to just be coming back in the reverse, right? So what we can do is we can combine these two paths. This is Q over H bar C, and it's going to be a closed path, BL dot A. But this, we just saw what this is. This is going to be Q H bar over C times total flux, right? We can use the Stokes theorem, and from the Stokes theorem, it's like area times area, B fields. But we know there's only B field here, which is like given by the flux. Then total flux is going to determine the total phase. So what this says is like total phase difference is going to shift. Then at any given moment, so if this is let me make it red. If this is the original interference pattern, depending on the phase, you are going to just shift it like this. Or if the flux is in the other way, you are going to shift it like that. It's not really important which way, it just shifts a little bit. And now we can come back to our original example. So our original example was this circuit, which of course didn't know about interference, but we say that if electrons are waves, it has to know about interference. And suppose we put like a flux in the middle. Again, this flux, if it's only in the middle, should not influence electron classically. But we know quantum mechanically it's not the case. Now we know there's like some interference pattern here, and if there's like this is exactly like a double slit experiment, right? There's no difference. If the interference here is going to change with the flux, one can anticipate that total EQ is also going to change with flux, right? Because for example, if you are increasing, like if you are at a point where you have like a constructive interference, by like here for example, by just changing the flux, you change from constructive interference to destructive interference, but this is going to decrease propagation, this is going to decrease conductance. Whereas if you were originally at like a destructive interference, I don't know, the arm lengths, who knows what they are, but they are going to, the phase difference is going to shift, and we can anticipate something like that. If this is G as a function of phi, and this is phi, we anticipate some kind of oscillation here, right? And the oscillation here, what we have seen from this ring, is going to be, the period of ring was 1, but it was phi over phi 0 was 1, then the period of here is going to be order of phi naught. And I think I have an example of this somewhere. Okay, here is the experiment. So what they do is like they form this exactly the same ring, and they put some leads, they connect to these leads and they pass a current, and as a function of flux, of course, how can you realize a flux right in the middle? It's like another technical issue that requires a lot of experimental control. But if they do that and then they put the flux, what they see is like, okay, so this is I think this is conductance G as a function of flux, and you can see there's like a order of phi naught oscillation in the conductance as we anticipated. So okay, so this is what Ahoronov-Bohm effect is: oscillation of conductance with the flux trapped in the circuit. So let me make a couple of remarks and finish it there. So if interference influence conductance, like even like moving like a single impurity, like motion of even a single impurity right? If the electron propagates through some impurities, that even if you change just one single impurity, it's going to change the total path of that electron, and it should also influence the conductance. A tiny change should have like a effect on conductance. Motion of even a single impurity should change conductance. And we'll see that this is actually indeed the case, and this is called universal conductance fluctuations, UCF for short. So this is one thing we don't expect classically. Another thing that we'll see is like if we have a narrow channel without any impurity, right? Classically, conductance or resistance is due to impurities, but if you don't have any impurities and like you have like a narrow channel, there should be zero resistance. But we are going to see, like, due to interference, there will be quantum of resistance. Even without any, like, even like a wire without any impurity is going to have a resistance. And that means, like, typically, like, when resistance of a wire is due to impurity, we say that like it is like a local quantity, because it like every point in the wire has its electric field, and that electric field is going to have like a corresponding current. But if even without like a impurity we have like a resistance, that means like the resistance is like a non-local quantity. It's like a property of entire device. So this is non-local conductivity. And lastly, there's the question, why don't we see these things in real life? We don't see it in this real life because these effects are quantum effects. They require low temperature, I don't know, less than a few Kelvin. But that's also like smaller devices, right? I don't know, like almost nanometers scale maybe. So I think this one has probably micron size. Let me say it like sub-micron, because if your device is bigger than that, there is what we call like a phase coherent, like there are like things like phonons, electron interaction, and there are like some impurities with internal degrees of freedom. They can like destroy the phase coherence, and then phase coherence is destroyed. That means no interference, and that means you cannot see any of these effects. So for this to happen, you need to have one way or another some kind of inelastic scattering. And if you can like prevent that, you are going to observe this. Okay, maybe I can stop here and continue next time.